Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. In the first half, we talked about transformer. Transformer, of course, is very related to the other model, which is actually our focus, which is BERT, because as you will see, BERT is built based on the transformer. So what is BERT? BERT is a language representation model. It stands for bidirectional encoder representations from transformers. So it is very clear that just from the name that it is based on the transformers, and it is only based on the encoder side. So in the transformer we saw two sides, right? The encoder and decoder. And the actual goal of the transformer is to have a sequence-to-sequence task. So given an input sequence, I want to get an output sequence. But the goal of BERT is not to do a task like that. It is to understand the language, is to provide an encoding of the input, okay, which of course we call it in our terminology, we call it embeddings or contextual embeddings. So the actual goal of BERT is to learn good or high quality contextual embeddings from the input. And with the embeddings that we will learn, we can use it, as we will see, in different tasks. And actually in the paper that showed BERT for the first time, the authors showed that with this model, they outperformed many state-of-the-art techniques in several tasks. So it is really very effective model for language understanding. So as we said, it is based on transformers. It is based only on the encoder side. So there are two, at least in the original paper, now I think there are more. There are two versions of BERT. One is called BERT base, which has only 12 layers of the encoder layers, the encoder stack. So 12 layers. And BERT large has 24 encoder layers, with of course different parameters, with different sizes. I mean, the size of the embeddings that we get out of each model here is different. It is larger a bit than the transformer. The feed-forward networks, they have two versions, and I'm talking about these two versions here, base and large. One that provides 768 dimension for the embeddings, which is the hidden units. By the way, the embeddings always are the output of the hidden layers. The output of the last layer, the output layer, is usually for a specific task, but the embeddings are taken from the last hidden layers, usually. Some studies actually showed that using embeddings or using the output of the other layers even might be helpful. Okay, but when we say using the embeddings from BERT, usually we mean the output of the last hidden layer. So for each word, we have embeddings of size 768 from BERT base. From BERT large, we have 1024. In the transformer, we had I think 512 always. In BERT, we have 12 and 16 attention heads in these two versions versus 8 in the transformer. Anyway, so these are just numbers to compare between BERT and transformer. Let's now talk about BERT in more detail. So as we said, BERT is based on the encoder stack of the transformer. So we have input sequence, and we have, for each word, we have the output embeddings for it. So the blue ones here are the embeddings for the specific corresponding word or token in general. But you notice that there is a special token that is given usually at the beginning of the sequence, which is called CLS, short for classification. So that's a special token that is usually given at the beginning, and the corresponding embeddings for that token usually is used as the embeddings for the entire input. So this is like the summary or the embeddings of the entire sentence, okay, if we are talking about one sentence here. And we will see that this is very useful for, or that showed that to be very useful in several classification tasks. But in general, for each input token here, or word, word for simplicity, but it's actually token, we will get a contextual embeddings vector for each word or for each token, okay, including the CLS token, which is a special token, including other special tokens that we will put in the input. The size of the input is limited, as we said. I think in the transformer it is 512 tokens only. We cannot put more than that for efficiency reasons. So we will have to deal with that, as we will see inshallah later in the lecture. But that's the architecture. Now, how do we train, or how we can use BERT, or how we train that architecture? Now, forget about the decoder. So we don't have the decoder. We just have the encoder. So you can think of BERT now as a model that will give us embeddings, like what we saw in Word2Vec and GloVe and Elmo. Okay, but that's more powerful because it was shown to be very effective in several tasks. Okay, and that's of course because of the architecture of the underlying network, which is a transformer. So remember that this is the left side, the encoder side of the transformer. So it's like half transformer with all the self-attention layers and feed-forward layers, sub-layers that we talked about in the transformer. Just to give you a quick idea of how BERT is used, let's assume that we learned BERT model. When we input a sentence like this, we for classification tasks in particular, we use the embeddings that correspond to the CLS token, the first token, okay, which is considered like the summary of the sentence, the embedding summary of the sentence. So instead of getting embeddings, aggregating embeddings for terms, of course we have an embedding for each term, but instead of aggregating it ourselves, this is learned embeddings for this sentence. So you can take this embeddings, and this is very important for several projects in the course, asking about how we can use embeddings. These embeddings can be used as an input to any classifier. So you can use a feed-forward network, you can use SVM, you can use any classifier, okay? And you can think of this as a feature vector now. Okay, usually it is used for classification. So you give it to the classifier, and that classifier will learn a model based on that input, of course, for several training examples, and will learn the classification probabilities. Here, we want to classify whether this is a spam email or not. So it will give us, the classifier here will give us these probabilities. But this classifier is not part of BERT itself, and this is a very important point to understand. So BERT is a model to give you embeddings, to give you a representation for the sentence, or two sentences as we will see, for the input. Okay, so embeddings for the input, whatever the input is, it will give you embeddings for each token in the input, plus special embedding for the CLS token that can be used as an overall representation for the entire sentence. Now, given that, you can do whatever you want with it. You can do retrieval, you can do classification, use it as you wish as an embedding for the entire sentence, and you can also get the embeddings for each term. And of course, these embeddings are contextual embeddings because it depends on the entire sentence. And if you have the same word in two different sentences, you might end up with two different embeddings for that word. Okay, as we mentioned I think 2 lectures before when we talked about Elmo. This is not like Word2Vec. Word2Vec, the embeddings are static. Okay, these are contextualized. To get an embedding for a word, you have to give it in a sentence. Okay. Any questions so far? Because we talked about the details of BERT. So this is showing you how to use it in a very high-level description, and the architecture of it in general is the encoder stack. Any questions?
Yes, excuse me, Doctor. Which one more powerful, BERT or Elmo? The same.
To my knowledge, BERT was shown to be more effective in several tests. So if you have the choice, if you can use both, then I would recommend you to use BERT first.
Okay.
Okay. Any other questions? Okay, so let's go into the details of BERT. So let's talk about training, how BERT is trained. BERT is trained in 2 phases, okay, or 2 steps. The first step is called pre-training, and the second step is called fine-tuning. So pre-training is pre-training the language model itself, okay, the BERT model itself. So we train it, as we will see, using 2 tasks. We will explain one of them, but out of that, we will get embeddings for, we will get a model that we can use to generate embeddings for any sentence. This is what we call pre-training. Pre-training is done using self-supervised approach, very similar to the way we, I mean, in principle, the way we train the Word2Vec. Okay, we'll see how, but it is self-supervised. It's completely unsupervised. We don't use any manually labeled data. We just use data, text data that is available. That's why we have here something like infinite training data. We can train it on any collection of text. Okay, so that's pre-training. Out of this phase, of course, we'll talk about how the pre-training works, but out of this phase, we have now a pre-trained model. Okay, we call it pre-trained model, which is BERT large, BERT base. I think there are other versions. These are the pre-trained models. We don't have to pre-train it again because that's very expensive. Okay, lots of computing power is used to learn that language model or that language representation model. So we don't have to everyone to do it from scratch. We can use the pre-trained model. But watch out for the difference between this and Word2Vec, for example. Word2Vec, it's not the model that we use. It is the embeddings directly. Here we use a model to use to generate embeddings for a given sentence. Okay, so it is pre-trained model, not pre-trained embeddings. That's a big difference. Now, after we pre-train, any questions?
Excuse me, Doctor. Just a question. Can we start with the Word2Vec, or just we can?
Yes, exactly. Yes, so, we can start. Yeah, in pre-training, you can start with Word2Vec and build on it. Yes.
But this is considered as supervised when we start with Word2Vec, because it has some features or some embeddings.
Okay, supervised is always means that there is a label. Okay, there is a label for the test that is manually given. Okay.
I understand. Yeah.
In that case,
I thought that. Yes. Okay. Thank you.
Good. Right. After pre-training, now we have the model. This model, you can think of it as a very general model. It understands the structure of the language, but it is not specific for a task. So you can further train it. We call that fine-tuning for a specific task. So that same model can be fine-tuned for a classification task, can be fine-tuned for ranking task, can be fine-tuned for machine translation task, for example. You can do whatever you like, okay, given of course the limitation of the model. But for every task, you have to fine-tune the pre-trained model for that specific task. So this is like learning a lot from the training data, learning a lot about the language. But now if I want to do a specific task, I have to tune it a bit to learn something specific about that task. This is what we call fine-tuning. So that's the second phase. So you see here, it is one model, but that model is used to learn multiple tasks. Okay, so one model can be fine-tuned for question answering, one model can be fine-tuned for named entity recognition, natural language inference or understanding. So different tasks, each one needs, or each one now has some labeled data. So this is now actually the supervised learning step. Okay, so fine-tuning, you have to have labeled data from the domain of the task. But pre-training, it is pre-trained on unlabeled data from text, because it learns the language. It doesn't learn a specific task. Okay, but fine-tuning is about learning a specific task. So here you see here that it's like infinite training data. We can keep pre-training it if we have more data. Here we have some labeled examples. Usually there are few, of course, relative to the size of the training data here. This is always few, like hundreds or thousands, sometimes tens of examples, just to fine-tune the model for that task. Now, when we say fine-tuning, we are actually changing the BERT model itself, but for that task. Okay, so we start with the pre-trained model, and then we update the model based on the task that we want to learn. Is this clear? Because this is very important to understand. Any questions on that? Do you understand now the difference between pre-training and fine-tuning?
Doctor?
Yes.
Yes, pre-training is the offline process and fine-tuning is the online, or no, all of them are offline?
It depends on what you mean by online and offline here. Or what do you mean by online here? When you use the
Mainly when
model
we
itself?
have the query, yes, when we have the query and we want.
Type. Yeah, forget about ranking now because we talk about ranking later today. But let's say that I want to use BERT to do sentiment analysis. I want, given a sentence, I want to train it to tell me whether this sentence is positive or negative. Okay. I will, of course, train the model first. So usually training is offline. So I will start with the pre-trained BERT model. I will fine-tune it on labeled sentiment examples, and that will be done offline. Alas, I have now a model that is specific for sentiment analysis. Now, when I use it in reality, I will use it online, of course. Training is done. Is that clear now, Mariam?
Yes.
Okay. Yes, Muhammad?
Yeah, I apologize for this, but I'm kind of confused. What is the difference between self-supervised and supervised? Because at least the way that they're written, they're confusing.
Okay, self-supervised means that you don't have external manual labels. Yani, do you remember how Word2Vec was trained?
But
did we have manual labels for Word2Vec, for training Word2Vec?
Essentially, like they're auto-generated from.
Yes, it's auto-generated. Exactly. We don't need a human to go and tell me that this the label for this sentence is that, or the label for this word is that. Okay, so it is the labels. Of course, we use supervised approach. Okay, but the learning itself is completely unsupervised because we don't need any manual labels. Okay, so this is called self-supervised. So we actually, the approach is supervised. The approach needs labels, but we generate the label, we auto-generate the label from the data. This is exactly what we mean by self-supervision.
I see.
Okay?
Thank you.
When we say supervised without self-supervised, supervised means that we have to have the manual, we have to have the labels, okay? And the labels are usually, in that case, to distinguish between self-supervised, in that case, it will be manual labels, okay? Any other questions? Okay, type. Now, let's get into more detail here. Let's say that the input is here at the bottom of the slide. We have this string, the bank makes loans to clients. Okay, and there's a dot here, that's the end of the sentence. So we represent that input this way. We start with the special token, CLS token, and then we have the sentence with the dot, and then we end the sentence with a special token called separator. Okay, each of these tokens again will be input directly to BERT. Remember, BERT is the left side of the transformer. Does the transformer get the words directly? Of course not. It will get initial embeddings, right? So we'll have to have the token embeddings first. Okay, so that's what we saw in the transformer. Then we also have what we call segment embeddings. As you will see, sometimes we can put two sentences as an input to BERT. Okay, in that case, we have to identify which tokens belong to the first sentence and which tokens belong to the second sentence. So that's what we mean by segment embeddings. Okay, so it will be like ones in the let's say 0 and 1. 0 means the first or 1 and 2. 1 will be the first sentence, and 2 will indicate the second sentence. Okay, so that's segment, what we mean by segment embeddings. We also have the position embeddings. Okay, all of these that we talked about in the transformer, all of these will be summed, and that will provide the input for the encoder side of the transformer. Out of all the architecture of the encoder stack, we will get an embedding vector for each of the corresponding inputs. Okay, so for this token, so that's the input embeddings for this token. This is the output embedding for that token. So that's the contextualized embeddings for that word in that sentence. Okay, and this one is the contextualized embeddings for this word in that sentence, and so on. This one is very special. This is the embeddings for the CLS token. This is usually considered as the embeddings for the entire sentence. So if you want to classify this sentence, then you can take this embeddings as an input to the classifier. Okay, even the separator has an embedding. So every input token here, we can get the embeddings for it. Again, if you don't remember, the embeddings is just a vector, high, not very high, but in BERT, I think, as I said, it's 768. If I remember, I won't. Yeah, so that's in BERT base, it's 768 dimensions. In BERT large, it is 1024 dimensions. So this is what we get out of BERT. Okay, for each input token, we get the embeddings vector for it. Okay, the size of that depends on which model we are using, base or large or whatever other models that were pre-trained. Okay, type. Now this is what we call the contextual embeddings. Now let's talk about how this is pre-trained. So what we saw in this slide is actually how we use the model. After we learned the model, so that's the model that is learned with millions and billions of weights here. Okay, billions of weights are trained, okay, to give us this embeddings. Now, if after we train this, we can use it that way. But how we trained that architecture, this is one of two tasks that were described in the original BERT paper. This task specifically is related to language modeling. So this is called masked language modeling. So what is that task? We have the original sentence, the bank makes loans to clients. Okay, dot. That's the original sentence, right? We want the, and this is very also similar to the idea of word-to-vec. We want the model to learn the structure of the sentence, so that if I masked one or some of the words in the sentence, in the input sentence, it will predict it here. It will give me embeddings for that. It will give me an indication that this word should be to. So that's what I teach, or what I want the network to learn. I want to mask one or some of the words in a sentence, and then the network or the model will tell me which one I masked. Of course, in the beginning, the model will make mistakes, and then with backpropagation, the model will be updated and so on until the model actually learns from the input data.
Excuse
from
me,
the
Doctor.
training data. Yes.
What do you mean by mask?
Mask here means put special embeddings here that indicates that this word doesn't exist. It's masked, it is hidden. Okay, so that's a special token here. Instead of putting the embeddings for to, for the word to, that's the original word in the sentence, I put special embeddings that indicates that this is hidden. Okay, for the input. So this is like masking that word. That word now is not part of the input anymore. For training, okay, in training, this is how the model is trained or pre-trained. Okay, and that's all actually doesn't is not done only on one word in the sentence. It can be done on multiple randomly. So that's a bit of difference between this and word-to-vec. And also word-to-vec use just 2 layers. This is of course much larger than word-to-vec. Anyways, just that there is some similarity in the task, but it is actually different. Yes.
So every time one word will be masked, so it will
not only one.
Word?
I think there was a, if I remember correctly from the paper, it's like 15% of the sentence, of any sentence.
And the model should predict that word, or?
Yes, predict all the words that are masked.
Oh, okay.
Okay, so in the corresponding embeddings here, that should be that should indicate if I think I have this next slide. Yes, so actually not next animation. So here we have a layer, okay, that takes the embeddings of the size D. Okay, remember, all the embeddings here are of the same size. So let me first remove this. Okay, so the embeddings of size D, we will have like a layer that will give me V numbers. Okay, what is V? V is the vocabulary size. Again, let's say that the vocabulary size is 1000, so it will give me 1000 numbers here. Okay, and then I will use softmax to convert these to probabilities, and the max, the one that with the maximum probability, I will consider that this is the output of the this is the corresponding to the word that is predicted for this training example, for this word. Okay, and based on that, I can see whether this is correct or not, and based on that, I can update the model. So this is how this is done. So if I get this, again, remove. So if I get this probability distribution over the vocabulary, okay, and this is of course the maximum one. Let's say that this is it is not the true word, then of course the model should be updated. Okay, so we'll compute a loss. Loss, of course, this should actually, I think this is wrong. That should be, I think that should point to the maximum here. Okay, because the loss will be computed with reference to the maximum one. Okay. Anyway, with this loss function, we will update the model, okay, based on what is the predicted value out of this probability distribution. And that will be done with every masked input. So if we masked this word also, so if we put a mask here, if that word is not there, then we'll also have the distribution for this from this embeddings, from this output layer of that, from that token, and we also compute the loss. Okay, we see if that maximum is the word corresponds to the word bank or not. If not, then we will update the model. Okay, so that's one of the two tasks that were used to train BERT. Any question about this? Is that clear?
Sorry, doctor, but just to clarify
Yes.
this point, the output from the output here is embeddings, like a matrix. Then we will use the loss function to get the probability.
Yes, there is an output. Of course. Okay, let me clarify one thing. I said that earlier, that whenever we say embeddings, that's the output of the last hidden layer. Okay, but there is an output layer. Okay, so that output layer has this for each token. Okay, so after the embeddings, there is an output layer that will give us this probability distribution, and that's what we use to update the model if there is any mistake. Okay, did I answer your question or still not?
Not clear. يعني after the output is embeddings like a matrix or weight, then from this weight we will calculate this
probability distribution.
Yes. And from this one, if it is correct, okay. If it's not correct, we will
update the model.
Yeah. Yes. Yeah, and V is the vocabulary, and D is fixed sized from the model itself, 502 or what's the numbers?
768, yeah, in BERT base, yes.
Okay. Yes. Okay.
And the vocabulary is the fixed size, also vocabulary size, the vocabulary that we have from the training data that we use.
Okay, thank you, Doctor.
Okay, you're welcome. Any other questions? Okay, fine. So this is again one example from the pre-training, but with more masks. So let's say that we have this sentence. Of course, we can train on millions of sentences, right? If we have lots of text documents, we chunk it into sentences, and with every sentence we do this. We do something like this. So let's say that this is the sentence. I will mask some of the words. So I masked here the word century. I masked the word Europe, okay, randomly, okay, 15% of the tokens in each sentence, and then pass it over BERT. We get the embeddings for corresponding to the masked tokens, okay. Then we do the this linear layer, which will convert the which is on top of the embeddings, to convert it to numbers, and then softmax to convert it, I mean, the number that can be positive or negative, and then convert it into probability distribution. This is an example of the probability distribution here. Okay, so you see that essentially that model is now learned in a correct way. Essentially is the highest, will have, essentially has the highest probability in that, so that means that this prediction is correct. Here also Europe has the highest one, so that's correct. Okay, if it's not correct, of course, we'll go back and update the model accordingly using BERT propagation. Okay, so this is this is how pre-training is done. Okay, now again, pre-training is done in a completely unsupervised way, or self-supervised, using lots of text. We don't need to do any labeling by ourselves, as Muhammad earlier mentioned. This is completely auto-generated. Okay, we randomly mask some of the tokens, and then we provide these as labels. Okay, the ones that are masked as the labels that we want to predict for that example. And of course, we need lots of compute power. Okay, lots of, if you heard about the TPUs to do this. And this is, of course, not available for everyone. Maybe available at big companies like Google, who had this this model, but it's not available for everyone. Okay, so it was really nice that Google open sourced the model. Okay, in terms of the model itself and the code, the source code that was used to pre-train the model, and the source code also that is used to fine-tune the model for the tasks. That really made big and fast adoption of this model in several tasks, and showed everyone that yes, this model is really effective, and we can reproduce the results that were reported in the original paper. Okay, any questions about pre-training? So this is an overview of pre-training. So we have the transformer, but the encoder side only, but with much more of parameters. That's the weights in the network. It's a bit bigger than the encoder side of the transformer, and lots of text. Wikipedia, web, books, many things. You can put whatever you want here to learn. As you put more, probably you will learn more. The model will learn more the structure of the language. And of course, lots of compute power to get the pre-trained model. So with that, we are done with pre-training. Any questions before we switch to fine-tuning? All of that, by the way, has nothing to do with IR yet. Okay, but since BERT was shown to be very effective in ranking tasks, of course, we have to give you a quick overview of how it works. Any questions before we switch to fine-tuning? So pre-training is clear? Should I ask questions? Let's have a quick quiz here.
So till this point, we can find it open source in Google. Like whatever we want, we can just retrieve it from Google, the model itself.
Yes, the model is available. Even the source code that was used to pre-train it and fine-tune it is available. Okay, now let's switch to fine-tuning. So we said that we have now a pre-trained model, okay, and we want to use it for specific tasks. So in the original paper of BERT, the authors showed that BERT model, at least in that paper, was used in 4 different ways, or four different types of tasks. The first one is single input classification task. single input classification task. Like what? Like sentiment analysis. I am given a sentence. I want to know whether this is positive or negative or neutral. Okay, so how is that done? You pass the sentence with the CLS and the separator special tokens, and to get the CLS embeddings for that sentence. Then you, with the class label, so now I have, remember that this is part of the training, right? Now fine tuning is supervised, so we have to have label data. So imagine that now I have this sentence, okay, like this car is fantastic. Okay, fantastic. So this sentence is positive. So I have the label for it. I have the sentence. I pass the sentence here as an input. I get the CLS embeddings. Now I have the label also. Now I can train a classifier here on the embeddings that I get from the CLS token. Okay, so using this, I can train a classifier. Actually, in BERT paper, they always used linear classifier, but of course you cannot. You don't have to stick to that. So linear classifier with softmax layer to get probabilities. So in this case, I will have just two classes, right? So I will have output layer of this will be just two nodes to get a probability, or actually three if we have positive, negative, and neutral. So we have three. So three numbers here, let's say 0.6, 0.4, 0.1, oh no, sorry, 0.6, 0.3, 0.1. These are the probabilities that we got. Okay. So based on that, we will train the classifier. Okay, and with changing the model itself. So that's what we mean actually by fine tuning. Okay, so fine tuning. If I will only train this classifier, this is not fine tuning the pre-trained model, right? Because we are not changing the model itself. But with learning that classifier, we also update that model based on the loss function, whatever the loss function that we use to train that classifier. Okay, so now the pre-trained model will change, but will change for the task that you are training it for. Okay, or based on the label data that you provide for that task. So you learn this linear layer, and you will also update the weights here. Type. Now, after fine tuning for that task, I want to use that model. Should I use BERT only, or the classifier only, or both? What do you think? Any answer? After I fine tuned it. Yes.
Both.
Bashir? Both. Why is that, Bashir?
Because when I rank the model, I need the label, يعني embeddings with labels.
No, I'm not talking about fine tuning. I'm talking about now using the model to classify a new unseen sentence. Yeah, let's say that I said that's great. Okay, I want to know the sentiment of this. Okay, so what should I use now after I fine tune the model? What are the steps to get the label, the final label of that new sentence? I have to pass. Sorry, go ahead. Ahlam?
Yes, both, because we need the CLS, then we will need the classifier to classify.
Exactly. So you will pass the sentence here to the original BERT model or the fine-tuned model?
Fine-tuned model?
The fine-tuned model, yes. Okay, the fine-tuned model, because the fine-tuned model is an updated version of the pre-trained model, updated for your task. So you'll pass the sentence through the fine-tuned model to get the new embeddings for CLS, then take this as an input to that classifier to get whatever classification decision that you want. Okay, so that's for what we call single input classification tasks. Any question about this? Here, in general, you can use any classifier. Okay. In the BERT paper, they just used a very simple one, and they showed that they can outperform the state of the art in many classification tasks. So that was really amazing. With very simple classifier here, which is linear classifier, they managed to get better than the best system that was before BERT in many classification tasks. Any questions? The second type of tasks that was shown in the paper is two input classification tasks. Two input classification tasks. That means that you will have two sentences as an input to BERT. So you put the first input, of course, first CLS, the first input, then the separator, then the second, the first sentence, then the separator, then the second sentence, then another separator. That now still within the limit of the 512 tokens. Okay. So you give these two sentences. How can you distinguish between these two sentences? You will use the segment encodings. Okay, that we discussed in one of the previous slides. So you give these two sentences. Now you pass them to BERT. That's the input, the full input to BERT. From that, you will get again the CLS embeddings. So same thing that you did here, you will have also a classifier here that you will need to train. Okay, type. What kind of tasks is that? And as an example, if I want to know whether one sentence is a paraphrasing of the other one. So these two sentences actually mean the same thing, but one is a paraphrasing of the other. If I have labeled data for that, then I can fine-tune BERT for that specific task. Okay, in that case, we have it's a binary classification. So the CLS token will just be an input for a binary to a binary classifier that will tell us whether this is true or false, whether they are paraphrasing of each other or not. Okay, so that's an example of two input classification. Yes, Marina.
In this level, tens of examples is enough to train to find tuning the BERT?
Sometimes, of course, as you have many examples, that will be better. Okay, but they show that for some tasks, few examples were enough. They call that a few shots. Okay, you just need just few examples. Okay? But of course, as you add more labeled examples to train your classifier and fine-tune the model, of course, you will get better performance. But reasonable performance with few. Remember that why do we need few here? Why do we need fewer than usual? Can anyone answer me? Why in this case? Because usually in machine learning, we talk about many labeled examples. We need really large training data to learn a good classifier. But why for BERT, maybe much fewer than that we can use? Why is that?
Maybe because we're using the pre-trained model.
Paula? Sorry?
Maybe because we're using the pre-trained model.
Yes, because the pre-trained model already understands the language to some extent. So we pre-trained it on so large data already. Okay, although it's not for the task, but every task depends on some standard knowledge, right? And if you think about it, we don't, even in reality, as humans, we don't learn each task independently, right? We have some core knowledge that we have, and then based on that core knowledge or core understanding, we learn some tasks, right? We don't take any years to learn a new task. This is a cumulative experience, right? So the pre-trained model idea is capturing this idea. We pre-trained the model already on so much data. It understands the language. Now we can use this understanding with some supervised learning with some labeled data. Now it can learn specific task. Okay. Any questions? Okay, the third type is single input sequence labeling tasks. This is something like given one sentence, I want to, as an example, of course, I want to tag or label each token in that sentence, whether this is, for example, a name or not. Okay, so this is called named entity recognition. So I want to get a tag for each token. Okay, so in this case, I will also have the labels for each tag, for each word, and from the embeddings for each word, I can train a classifier. So similar thing, but now I have a label for each token. Not only, so I will not use only the CLS. I will not use the CLS actually embeddings. I use the embeddings for the specific for each token. Okay, to learn whether to train whether this is a name or not, or whatever the tags will be. So that's single input sequence labeling. There is also two input sequence labeling, something like machine translation that we saw before, or question answering. Okay, actually not machine translation, because machine translation you will not. It's one input and one output actually. Sorry, so that's not two input sequence labeling. Two input sequence labeling means you give two sentences, and then you get labeling for part of them. So an example here is question and candidate answer. So let's say that this is a question and this is a passage, and I need to get the answer within that passage. Or this is a claim, and this is related to one of the projects. This is a claim, and this is a passage, and I want to get an evidence for that claim, supporting or refuting that claim. Okay, so I give these two sentences or passages within one input, okay, as an input to BERT, and then use the embeddings for the second sentence, because that's where I want to get the answer, and use start and end span. So the labels here will be beginning and ending of the answer. Okay, so I will if I have multiple training examples on that, then I can train a model to learn the beginning and ending of the answer. All of these tasks are described in the BERT paper. So if any of these tasks are related to your work, then of course all of you, whether it's related or not, all of you should read the BERT paper, and you should focus more on the section on the tasks that are related to your project. Okay. Fine.
Excuse me, Doctor.
Yes.
One small question. So the input, yes, it can be sentence, it can be a document, it can be passage, it can be not only tokens, yani not only words.
It is words. It's a string of maximum 512 tokens. Now, in that string, you can put one sentence, you can put one passage, you can put two passages, whatever can fit within this size.
And each input of size 512, each input, each one, not all?
No, BERT takes one input only, Ahlam. That input is of maximum size of 512, but you can within that 512, you can put one sentence or, I mean, one input, one. The problem is that we are using the word input in different ways here. Okay, let me try to clarify that. BERT takes just one sequence, okay, one sequence, okay, of size 512 tokens. Now, within that sequence, I can take part of it to be the first sentence, and then there is a separator, then the second sentence. Still, the total of this must be no more than 512. Okay.
You mean, Dr.
Or it can be one passage.
Yes. Okay, I understand.
Is that clear now, Ahlam?
يعني as if the input is array.
Ahlam, sorry, Marina. Ahlam first. Is that clear?
Yes, clear.
Okay. I think Wathaq also had a question, or someone else before Marina?
Yes, Doctor, I have a question.
Yes, go ahead.
As for two input classification tasks, there are many use cases other than paraphrasing, right? So, for example,
yes, of course.
if we want to.
Wathaq, if the input is two, you can do whatever you want, as long as you can represent your input within the sequence input of BERT.
Okay, for example, any
and
relation
as long
between
as you have labeled data. Yes.
Okay, so for example, if I want to get a relation between the first sequence and the second sequence, BERT or fine-tuning BERT, I can do it to perform such a task.
Yes.
Right?
Yes.
Thank
you. Okay, any other questions? Fine-tuning. No questions? Okay, type. The point that Wathaq raised, which is whether he or anyone can fine-tune for a new task. This is very important, because the examples that I gave, or even the examples in the paper that were given in the paper, are not everything. Actually, in that paper, there was no mentioning at all to any retrieval task. Almost all the tasks were natural language processing tasks, NLP tasks. But right after publishing that paper, researchers started to think about how BERT can be used for IR. In fact, in January 2019, you can see that this is like what we call leaderboard that shows the performance of systems on a specific task. So the task here was retrieval on a specific collection, and it was the beginning of the deep learning track in Trek. Okay, so if you look here on January 2nd, the best mean reciprocal rank measure for any submitted system. Second. Okay. The best system had the score of 28. Okay. In January 2nd. In January 7th, the best system had 35.8. So that's like 8 points increase suddenly with BERT. So before that, there was no BERT, okay? And that's a big jump. That's a really big jump that happened. BERT here was used for retrieval. So that was ad hoc search task. That's a standard IR task. Given a query, find me the relevant passages. It was a passage retrieval, I think. Yeah, passage ranking. And BERT was used for the first time. And just by the embedding, and you will see I hope, in few minutes, you will see how BERT was used for ranking. Although ranking was not mentioned at all in the original paper, but now you can imagine how it can be used. You can think of new even tasks for which it can be used. Of course, BERT was not the end of the transformers-based models. There are many models that came after BERT, but all of them are kind of a variant of BERT, improving it a bit with maybe different learning tasks, or making it more efficient, variants. But that's why we will not talk much about other variants, because the idea is quite similar. But BERT made or opened the door for using such language understanding models in IR. Okay, so in the middle of the night, 8 points, which is rare in IR, to improve that quick. The first BERT paper was posted, not even published, sometimes I think sometime in November or December 2018, and in less than 1 month, it made a big jump on an IR task. This is now in March 2021, so 2 years after BERT. If you remember here, that number, it was 35. That number now, based on models that are mostly based on BERT and its brothers, now if you look at the leaderboard, most of them are BERT based, and the numbers are still increasing. And that's all by BERT and its brothers or sisters maybe. And BERT actually was adopted not only in research, but by commercial search engines. Actually, officially, Google said that BERT made a big difference, and it is now used since, I think, sometime in 2019. It is used in Google search, and also Bing mentioned that it is using some form of transformer models. And you can see here in these two examples that there is something semantically happening in understanding the query versus the documents that were written. So that was a motivation, I think, for us to study how BERT can be used for ranking. Let me ask you, after we gave this introduction, how do you think BERT can be used for ranking? Based on the 4 ways, or at least the examples that we gave, how can we use BERT for ranking? Hamad?
I can definitely see query expansion as a utility. We can relate.
It can be used in a much simpler way than that. Okay, we'll talk about query expansion hopefully next time, kind of document expansion actually. But that's not the simplest way to use BERT for ranking. That was not the way that they used to get this 8-point jump. Any simpler ideas? That is very similar to what we did already actually in fine-tuning. Any ideas?
Maybe if we take the embeddings, like it's and calculate the similarity between the it's like a query, and we will make the BERT for this query,
Yes.
and get the embeddings, like a vector for this query.
Okay.
And then we will see the similarity between this vector that comes from the BERT and the vector from the document.
Okay. So I got your point. So so what you did, let me try to make sure that I understand what you said, Ahlan. So you said that, so first in retrieval problem, how many inputs we have? We have a query and we have documents, right? We have all the documents. We want to rank all the documents, right? Or we want to score all the documents. So what you said, Ahlam, is that we would use BERT to, so let's say that this is BERT. That's the pre-trained BERT, if I understood what you're saying. So that's the pre-trained model. So let's say BERT base. And we will use that to get embeddings for the query. So now this is the EQ. Let's say that this is embeddings for the query. And we will use it also to get the embeddings for every document. Or let's say that we will start, as we said last time, we'll start by BM25. BM25 will give us some documents, and then we apply them here. So let's say that I have a document D. I will get also the embeddings for that document. And then I compute something like cosine similarity between these documents. And that will be the similarity score between Q and D. And if I repeat that for several documents, then I can rank those documents given this similarity scores. Is that what you said, Ahlan?
Yes.
Okay, now let me ask you, before I give you my, before I comment, did we do any fine tuning here?
No, because
no. So we only
yes.
used the pre-trained model, right? We didn't do any fine tuning.
Yes.
Right?
Yes.
Don't you think that we should train or fine tune BERT on the problem that we are trying to solve, which is relevance?
Yeah, maybe like the first one, classifier, if it is relevant or not.
Exactly. Okay, exactly. This is the simplest way of using BERT for ranking. So we'll stop at that slide in this set and continue in another set. So give me a second. Do you want to have a, I think we should not break. I was planning to give a break for 5 minutes. I don't think we have time. So let me just open the other, give me a second. Okay, do you see this now? That's the new slides?
Yes.
What is the title?
BERT for ranking 1.
Okay, very good. Okay, type. Now, BERT for ranking. What is the simplest idea? The simplest idea is to convert the ranking problem into a classification problem. As Ahlam said, we will use something very similar to what we showed in the first type of fine-tuning. So when we convert ranking to classification problem, how many classes we have? Or what are the classes first?
Two.
Relevant.
Two, right? Relevant and non-relevant. Very good. If we, that means that we will pass the query and the document, right? So we need to pass the query and the document, both together in one sequence to BERT, get an embeddings, and then use that embeddings for fine-tuning. Okay, so we'll do fine-tuning as we did in single, actually it will be double input classification. We get query, we get passage or whatever you call it, or sentence or document, and then we fine-tune the classifier on the task using whatever label data we have in the relevant judgments that we have. Okay, so based on that, we get a probability for each document given the query. So we'll give these two to the fine-tuned model, and we get a probability, and this probability, of course, of one of the classes, which correspond to the relevant class, and then rank based on these probabilities. Okay, that's the main idea. We call this relevance classification because we are classifying for relevance. Okay, so now instead of giving only BERT one input in the sequence, so we give the query and we give the document. Okay, and we get that's now the fine-tuned version. So let's call it BERT prime, which is the fine-tuned using the labeled data. We have labeled data, right, which is the pairs, query, and documents that are relevant, and also we have negative examples, which are documents that are not relevant for the queries. All of this from the relevant judgments that we have, and we get a score, probability of relevance, given this query and DI. Okay, and we rank the documents based on these probabilities. Okay, have we heard about that before in learning to rank? Do you remember that we said something similar in learning to rank? We studied learning to rank last week, right? Hello? Do you hear me?
Yes. You maybe mean the by something.
What is by something? Type. First, is that learning to rank problem? Isn't that the same setup of learning to rank? It is very similar, right? We want to learn a model for ranking, right? Right or not? Yes, we want to learn a model to do ranking. Okay, type. If you remember, in the previous lecture, we said that we have 3 types of learning to rank. We have point-wise, we have pair-wise, which I think Ahlam was trying to remember, and we have list-wise. In point-wise, we take one document at a time and compute a score for it, and learn how to compute a good score for it. In pairwise, we take 2 documents and we learn which one is more relevant. And in listwise, we take a list of documents and we learn how to rank them. Which one is this one of these 3? Is that point-wise or pairwise or list-wise approach? What do you think?
Point-wise.
Ahlam says point-wise. Anyone else?
I know I'm shooting in the dark, but wasn't that point-wise? Sorry, I mean pairwise?
Why is it pairwise?
Because we're judging based on the query and the document.
Ah, okay. When we said pairwise, we meant that we have pair of documents. Remember last time when we said this document is more relevant than that document? So pairwise here doesn't mean that you will take the query and the document. It means that you will take the query and pair of documents, and you need to say which one is more relevant to the query. Okay.
I see. Thank you.
So if that's the case, which one you think, Muhammad?
Then yeah, it's going to be point-wise because we only have one document.
Muhammad and Ahlam are saying point-wise. Anyone else?
It's point-wise.
Marina, point-wise. One more vote for point-wise. Okay.
Is it list-wise? Because multiple
Tayyib is saying
documents.
list-wise. Why is that?
Because we need to score the documents based on the relevance.
Okay, good. So you think that it is list-wise because we want to rank the entire list of documents, right? But here the approach is about the learning model itself, Tayyiba. The learning model, does it take one document at a time, or pairs of documents at a time, or the whole list as a whole?
Yeah, one at a time.
One at a time. Okay, so that's why it is point-wise. It's not list-wise, and of course it's not pairwise. Okay, so it is point-wise, And what we were supposed to discuss today, and inshallah next time, will at least the part that we were supposed to cover today is all pointwise, and that method is pointwise. So that's a special case of learning to rank. Right. Now, as we said last time, I think towards the end of the lecture, we cannot afford doing that for the entire collection, right? We have millions of documents, sometimes billions of documents. So we have to do we have to do it in two steps. So we'll do initial retrieval using some best matching or exact matching retrieval like BM25. We get some candidate texts or documents, and then we re-rank them. Okay, and the reason why we are saying re-ranking, because we already have a ranked list from here, but this ranked list is based on BM25, which is kind of lexical matching. It's kind of best matching or exact matching. Okay, like word overlap, as you know. So it's not a semantic matching. So after we get this candidate list, we need to do re-ranking to get the final ranked list. So our focus will be here, the use of BERT, at least the part that we will discuss is here. Okay, that's why it is called re-ranking. It's not just, of course it is ranking, but ranking of a very small set. Actually, it is re-ranking that set that we got initially from that retrieval. Okay, there are methods that started to use BERT for direct retrieval without initial set. This is called dense retrieval, and unfortunately I don't think we will have time to cover it. Okay, but it is in the book, of course, that we started to study today, which is linked in the readings. There is a chapter about dense retrieval if you are interested. So that's the setup now. We will assume that we have initial list retrieved using BM25 or language modeling or whatever the ranking model that we use. Then we re-rank that set using BERT or BERT-based re-ranking. Okay. Right. Let's talk about the first model, which is called mono-BERT. Mono-BERT is based on the idea that we already mentioned. So we put both the query and the text that we want to re-rank or we want to score together in the same sequence with the CLS in the beginning, with the separators, with the segment embeddings, with the position embeddings, with the token embeddings. We give that to BERT. BERT will provide us with the embeddings of the CLS token. We use we can actually, this is what mono-BERT used, just as BERT did in the original paper, using linear layer with softmax to compute the probabilities. We get these probabilities, we compute the score based on that probability. So SI will be the probability of the relevant class. Okay, and we want that to be the probability that based on which we will rank the documents. Of course, that's in the inference phase. In training phase, we use these scores with the labels that we have to fine-tune BERT. Okay, so training will be fine-tuning here. We will start with the pre-trained model. We fine-tune it on this classification task, as we mentioned earlier, exactly as we mentioned earlier. It's just a classification task. BERT doesn't understand that this is used for ranking. But the task that we understand is ranking. We gave the labels based on that. This is similar to what was asking about. BERT is not aware of that, but it will learn based on that new task. So now this task was viewed as ranking, as a classification task. We fine-tune BERT based on that and get a new fine-tuned model. At the time of retrieval, what will happen? We will have we run BM25, for example. We get a list of documents, and then for each document we pass it with the query to BERT to get finally this score. We score all of these documents and rank or re-rank the documents based on that. Is that clear?
I mean, one thing that's at least I got lost about is that how did we go from relevant and not relevant to a rank or some sort of a measurement between documents?
Okay, so you understand that the classification here is binary, right? Relevant or non-relevant, right?
Yes.
So the classifier here will learn two probabilities or two scores after we use softmax. Usually always the scores will be like probabilities. So the sum of these scores will be one. One score will be for relevant, one for non-relevant. So let's say that this score is 0.7. This probability is 0.7. Now this is the relevance score. This is the score of the document. The score of the document is 0.7. If another document got a score of 0.5, then this is less than 0.7. So that's now the score of the document, And based on these scores, we will rank all the documents.
I see. So the main difference is that unlike traditional categorization problems, we don't pick the more probable value and then give it to the so-called rank. Here we actually use the raw value.
We always use the probability that is given for relevant class, because that's the one of interest to us.
Thank you very much, Doctor.
You're welcome. Any other questions? Type. What is the problem with that? Is there any problem with that? Any issues with this setup?
Maybe I was thinking about we can't put a document. It's like only for a passage or something small.
Why? Why?
Because we have only 512 tokens.
Yes, very good. Yes, that's exactly a problem. That's a challenge. Okay, so MonoBERT was not fine-tuned on big documents. It was used just for passages. Okay, and passages, of course, 512, I think, might be enough, and was fine-tuned with that. Okay, so it was not fine-tuned with big documents. This is a loss function that was used in fine-tuning. So you will see that this is sum over all the positive examples. Now, if Sj, which is the score for a positive example, is 1, then the value of this is what? Log 1 is 0, right? So if all of these are correctly classified, then the loss of that part will be 0, which is what we want. If not, then the loss will not be 0, then the model will be updated. Same here with negative examples. We want Sj's to be 0, right? That's what we want the model to be, to learn. That for any negative example, the score that is, which is the probability at the class of relevance, should be 0. Okay, that's the best. So if it's 0, then this part will be log of 1, which is 0, so the loss will be 0. Okay, so that's the loss function for MonoBERT. But I agree, of course, with Ahlam that the main problem here will be the size of the input, because 512 would be very hard to represent document, long document. Okay, it can represent a passage, and don't forget that we have the query also, right? Or we don't have to. Do we have to put the query alongside the passage or just the passage? What do you think?
Yes, because we are counting the relevance between the query and the passage.
Yes, very good. So query has to be there. Both have to be there. Okay, the query and the passage that we want to score. Okay, without the query, then we didn't understand anything of the interaction or the relationship between the query and the document. Okay, or the passage. So the query has to be there. The passage has to be there. So this is an overview of MonoBERT. You give the query to BM25 using the inverted index. It will give us an initial an initial list of documents. Then you pass it to MonoBERT, and MonoBERT will re-rank it. Okay? Of course, in between here, we don't take the entire list. We take one by one, pair it with the query, and get a score for each one of these. Okay, so from that score, we will get the final re-ranked list of documents or passages here. Okay, is this figure clear? No, not clear. It's either clear or not clear.
I mean, I assume that what we're doing is trying to figure out how documents relate to each other.
No, this is just a very high level overview of how MonoBERT is working. So you see here that this is the input query, okay,
Yes.
and the input doesn't go to MonoBERT; it goes to a standard static ranking model like BM25. Okay, so BM25 will give us the initial ranked list R0. Then this initial ranked list will go through the second phase. Okay, but if you remember that the second phase doesn't take a list, right? It's pointwise. So it takes each document, pair it with the query to get a score for that document independent of the other documents. Now, if we do that for all these documents in R0 and then re-rank based on the scores of these scores, we'll get this final ranked list, which is R1.
So does normalization matter here or not?
What kind of normalization?
The relevancy score, since it's between 0 and 1.
It will always between 0 and 1.
So there's no use to try to normalize SFI.
No. Why do you need
Right.
that?
Just making sure. Thank you.
You're welcome. Any other questions? Type. Is that what you saw here on that slide? Is that part of training or part of re-ranking at inference time?
Re-ranking, not
The
training.
re-ranking.
After
Re-ranking. Anybody is saying training? So where's the trained model here?
MonoBERT.
Yeah, this one, this box. This box is the trained model. This box, by the way, has both parts. Okay, has BERT and has the relevance classifier. Of course, I made BERT much larger because it is much larger. Okay, so that's input here to BERT, and then the CLS tokens embeddings go to classifier, and then the classifier tell me SI for each pair of query and document. Okay, is that clear?
Yes.
Okay. One last thing. the introduction of BERT made, as I said, made a big jump in the performance. So in the deep learning track 2019, if you look at this this table, you'll see that the performance NDCG, I know that now, I think you understand what we mean by NDCG and what we mean by MAP and what we mean by recall. All of these measures are known now. BM25 got 0.506 NDCG. When we used it with monobert, we got 0.738. So that's a big jump. Okay, and similar jumps in the other in MAP, in mean average precision. Okay, why didn't we get similar jump in recall? So
Because it's the same number of relevant documents we have, but we re-rank it.
Very good, very good. Okay, excellent. Muhammad, was that your answer also?
Yes, since we use BM25 to retrieve the document, so the recall will always stay the same.
Yes, exactly. We were just re-ranking the order of the document based on what we got from monobert. Okay. Here we used the relevance pseudo-relevance feedback model that was based on language modeling. Actually, that's not blind the ROCU. Okay, it's another relevance blind relevance feedback, which is also effective. It's called RMA3. When we used it with BM25, we got a bit better than 0.506. You see here, and small jump, but of course, when monobert is used, we got even a higher jump. Okay, so compare this with that. Of course, the comparison here is this is clearly much better, but with expansion, with relevance expansion, pseudo relevance feedback, it's a bit better, right? It's a bit better. And from point, small, very small jump. So that means that maybe sometimes we don't need this expansion anymore. The improvement that we got is really slight, between 0.738 and 0.742. Okay, but see the jump here.
And maybe because maybe the expansion will affect the efficiency also. So maybe
no, we are not talking about efficiency here, Ahlam.
Yes,
these numbers are effectiveness, right?
Yes, it's effectiveness, but I think if it is the effectiveness,
of course, efficiency will be is bad, طبعا, of course, because we use the elements. But the point here is that we didn't even need, forget about efficiency. Let's assume that it's very efficient pseudo elements feedback. Okay, the point here is that it didn't. Usually pseudo elements feedback gives you a better performance in terms of effectiveness. Okay? Usually, here it didn't. So the point here is that the semantic understanding or knowledge that the model got is not of a need to relevance feedback, to the information that we will get from relevance feedback.
Yes.
Okay? So that's
we understand the contextual the context of the query very well.
Exactly. Okay. Okay, so we'll have to stop here, but I hope that I motivated you enough to follow up on this, and inshallah next time we'll continue talking about how BERT is used. This is just the first one. By the way, this is the model that got the 8-point jumps in the beginning. So that's the model that started the wave of improvement in IR using BERT. Although it's very simple, as you saw. Okay, we'll stop here. We'll continue next time, inshallah. I hope that what we started tonight is good introduction for you to use in your projects. And I think the use is not that hard. With the concepts that we studied, with the open source code that is there, with the pre-trained models that are available, I think you can think of now how to use them already in your project, and inshallah next time you will see how they were already used. Any questions before we stop?
Well, thank you very much, Doctor. Today's session was very helpful, very useful. Thank you.
Okay, alhamdulillah. Thanks, Tayyiba. Any questions from anyone? I didn't hear all of you. I heard very few, but I hope that others are really with us since I don't see you, and also got a very good understanding, alhamdulillah, from that lecture, I hope. Any last comment? I wish we can be in the same classroom as we used to do since the beginning of the semester, but who knows where the best and here is. So I hope inshallah this will change, although I don't think it will change for next time, but at least in the summer inshallah will not be that case, I hope, and for sure inshallah in the next semester I hope that we will get back to normal setup, and we'll see you in class, because I really like to be in the classroom, and I don't like this online setup much.
Okay, thank you very much, Doctor. Thank you.
You're welcome. You're welcome. Okay, so we'll stop inshallah here and talk to you next week inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.